Hello class, today we'll be looking at chapter 10, which discusses moments of inertia, and this will be our last chapter that we will look at in this course. So let's consider a plate submerged in a liquid. The pressure of the liquid at a distance y below the surface is given by P equals gamma times y, where gamma is the specific weight of the liquid. The force on the area dA at that point is the change in F pressure times the change in A. The moment about the x-axis due to this force is y times that change in force. Right? The total moment is shown by this equation that we have here, where we have the integral of y times the change in F in the following equations. This sort of integral term also appears in solid mechanics when determining stresses and deflection. This equation becomes more clear when you take a look at this image in the top right here. This integral term is referred to as the moment of inertia of the area of the plate about an axis. Consider three different cross-sectional shapes and the areas for the beam R, S that we see over here. All have the same total area, and assuming they are made of the same material, they will have the same mass per unit length. For the given vertical loading P on the beam shown on the image we were just looking at, which shape will develop the less internal stress and deflection? Why? The answer depends on the moment of inertia of the beam about the x-axis. It turns out that section A has the highest moment of inertia because most of the area is farthest from the x-axis. Hence, it has least stress and deflection. For the differential area dA shown in this figure on the right, it can be represented by the following equations, where we have this variable J naught is the polar moment of inertia about the pole O or z-axis. The moments of inertia for an entire area are obtained by this following integration we have here, where it's our inertia of x equals the integral of y squared times dA, or inertia of y is integral of x squared times dA. Then we have the following for the J naught equation. The moment of inertia is also referred to as the second moment arm of an area and has the unit of length to the fourth power. So you would see it in meters to the fourth or inches to the fourth or millimeters to the fourth. You just got to remember that you always end up with the units that are to the fourth power. For simplicity, the area element used has a differential size in only one direction, either dx or dy. The results in a single integration and is usually simpler than doing double integration with differentials where we would have dx times dy. Now let's take a look at the step-by-step procedure for this. First, you choose the element dA. There are two choices, a vertical strip or a horizontal strip. And then some considerations about this choice are whether or not it is easier for it to be in vertical or horizontal. This will depend on the equations for what you're given for the problem. The second thing is to integrate and find the moment of inertia. For example, given the element shown in the figure, we have they have the inertia for y is given the following equation, and the inertia for x is given the following equation. Since the differential element is dx, y needs to be expressed in terms of x and the integral limit must also be in terms of x. As you can see, choosing the element and integrating can be challenging. It may require trial and error approach and a little bit of experience, but after doing some problems, deciding which one to use is easier. Let's take a look at our first example. It asks us to find the moment of inertia about the x-axis and the y-axis for the shaded area. And it gives us the curve being represented by y cubed equals x squared. Our integrations here, we have the inertia for x equals integral of y squared change in a, or change in the area. For dA is represented, we're using here a horizontal strip, right? dA is represented by 1 minus x times dy to get that area. And then doing some substitution, you end up with the following integral, right? And then you end up with your final answer for the inertia in the x direction as 0.111 meters to the fourth. Finding it for I of y, now you're using the integral of x squared dA, right? So we're switching from y squared to x squared. And then by solving the integral, you end up getting the solution 0.273 meters to the fourth. So for this next section, chapter 10.2, it looks at the parallel axis theorem for an area. So cross-sectional areas of structural members are usually made of simple shapes or a combination of simple shapes. To design these types of members, we need to find the moment of inertia. It is helpful and efficient if you can do a simpler method for determining the moment of inertia, such as cross-sectional areas compared to the integration method. This theorem relates the moment of inertia of an area about an axis passing through the area centroid to the moment of inertia of the area about a corresponding parallel axis. This theorem has many practical applications, especially when working with composite areas. So we can consider an area with a centroid C that has x apostrophe, y apostrophe axes. You see here on the top right what we're referring to, that passes through C. Right? The moment of inertia about the x-axis, which is parallel to dy, and the distance dy from the x apostrophe axis is found by using the parallel axis theorem. In the following equation, we have the inertia in x, right, can be represented by that equation using the definition of a centroid. We can also find what is being represented for the centroid of that y apostrophe, right? Now since C is at the origin of y apostrophe, we have that the integral of a at y apostrophe, a change of a equals 0, thus giving us the inertia of x equals to x, the inertia of x apostrophe plus a dy squared. Now I understand that these formulas may seem confusing, but when we get to actual problems, it starts to become clear. In section 10.3 talks about the radius of the gyration of an area. For a given area A, its moment of inertia x, imagine that the entire area is located a distance kx from x-axis, as we see in the image right. And then I of x equals kx squared times a, or it could be given as kx equals the square root of I of x divided by a. This kx is called the radius of gyration. of the area about the x-axis. This is a similar thing for, you can be fine for the y or for the o, right? So the radius of gyration has units of length and gives an indication of the spread of the area from axes. This characteristic is important when designing columns. Taking a look at section 10.4, it discusses the moment of inertia for a composite area. A composite area is made by adding or subtracting a series of simple shaped areas like rectangles, triangles, or circles. For example, the area on the right here can be made from rectangle plus triangle minus the interior of a rectangle. So we're just putting together simple shapes to get our final shape. The moment of inertia about their centroidal axes of these simpler shapes areas are found in most engineering handbooks, with sampling inside the back of the cover of the textbook. So you can find most of these shapes at the back of our textbook. Using these data and a parallel axis theorem, the moment of inertia for a composite area can easily be calculated. So steps for analysis here: you divide a given area into simpler shapes. You locate the centroid of each of the parts and indicate the perpendicular distance from each of the centroids to the desired reference axis. You determine the moment of inertia of each simpler shaped part about the desired reference axis using the parallel axis theorem, and you use that equation that we saw from earlier in 10.2. And then the moment of inertia of the entire area about the reference axis is determined by performing an algebraic summation of the individual moment of inertias obtained from step 3. So please note that the moment of inertia of a whole is just subtracting out a shape. And we saw that in a problem earlier, but we'll see that this can often be used for inertia as well as just normal shapes. Taking a look at our second example, it asks us to determine the moment of inertia of the area about the x-axis. So taking a look at the solution handed from the textbook, we have our composite parts, where figure A is our initial problem. You see that we have instead just a rectangle, and then you subtract out a circle in order to determine the overall areas, right? The moments of inertia about the x-axis are determined using parallel axis theorem, and the moment of inertia to formulate the circular or rectangular areas are given by those equations that you see there for I of x for both the circle and rectangle. For the circle, we have this using the parallel axis theorem, right? This is how you would execute that equation that we were seeing from before. And then this is what you would find for the rectangle. And since now we found the inertia of around x for the circle and the rectangle, the next thing we do is we subtract the circle from the rectangle to get our final answer of 101 times 10 to the 6 millimeters to the fourth as the moment of inertia for the area here. Taking a look at our final section, section 10.8, this section discusses mass moment of inertia. So let's imagine that we have a large flywheel, like what we see in the image above. In the picture, it is connected to a metal cutter. The flywheel is used to provide a uniform motion to the cutting blade while it is cutting materials. The question is, what property of the flywheel is most important for us to use, right? How can we determine the value for this property? Why is most of the mass of the flywheel located near the flywheel's circumference? Why is it mostly at the edge? These are some questions we're trying to understand by the process we're looking at in this section 10.8. The torque M for this band we see over here is initially at rest, its angular speed rotation begins to increase. Which property um, we'll call P of the fan blade do you think affects angular acceleration, what we call alpha, the most, right? How can we determine a value for this property? What is the relationship between M, P, and alpha, right? So let's consider a rigid body, the center of mass at G. It is free to rotate about the z-axis, which passes through G. Now, if we apply torque T about the z-axis to the body, and the body begins to rotate with angular acceleration of alpha, then T and alpha are related by the following equation, where you have T equals the inertia times alpha. In this equation, I is the mass moment of inertia, which is MMI, about the z-axis. This mass moment of inertia of a body is a property that measures the resistance of the body to angular acceleration. So that's what we're focusing here. This is similar to the role of mass in the equation F equals ma. So the mass of moment of inertia is often used when analyzing rotational motion, and this is done in dynamics. Now consider a rigid body and an arbitrary axis P shown in the figure below, right? The mass moment of inertia about the p-axis is defined as I equals the integral r squared dm, where r is the moment arm, is the perpendicular distance from the axis to the arbitrary element dm, and then the moment of inertia is always a positive quantity that has a unit of kg times meter squared, or slug times feet squared. So you'll have mass times length squared. Right? That's what you end up finding whenever you solve for the mass moment of inertia. Bringing back what we learned from the parallel axis theorem, just as with the moment of inertia for an area, the parallel axis theorem can be used to find the mass moment of inertia about a parallel axis z at a distance d from z apostrophe axis through the body center of mass g. This formula is shown as the inertia z equals ig m times d squared, where m is mass. This is represented by the image to the right. And the radius of gyration is similarly defined as k equals the square root of 1 over inertia over m. Finally, the mass moment of inertia can be obtained by integration by method for composite bodies, right? And the latter method is easier for many practical shapes. Taking a look at our final example for this chapter, example 3. The density of a solid for the figure below is 5 slugs per feet cubed. Determine the mass of inertia about the y-axis. Here it kind of looks like a cone, right? And it's being represented by y squared equals x. So here we're going to use a dis element. The moment of inertia will be determined using this dis element that intersects with the curve at an arbitrary x or y. It has a mass of change in m equals density times change in v, right? Because density times volume equals mass. This also equals density of pi times x squared, because pi times x squared is representing that volume times the change in y, right? Because that pi times x squared is just the shape of the circle, and then the dy is kind of representing the conishness, and then the density is just density. The moment of inertia of a disk about an axis is perpendicular to its plane. So we have that the inertia here is half times mass r squared. And when we put these equations together, we get that the change in inertia in the y direction equals 0.5 times density of pi x squared, change in y times x squared. For solving for this, when we plug in the initial equation we were given and the density, we find that the mass of inertia about the y-axis is equal to 0.873 slugs times feet squared. So that was our last example. If there's any other questions, feel free to reach out to me and ask me any questions in class. Thank you.